Now here let us study the forces acting on a falling body. The only two forces acting on a falling body are the weight downwards, mass times g, the acceleration of gravity, whatever the value of g, could it be zero at very high distances, and the resistance due to air, which is equal to k, rho density, a projected area, v square, the square of the velocity. That's why we cannot, you'll soon see why we could not perform the integration directly. Of course, I don't want to get into a long story. This force is the summation of two forces, the air friction and the projected static pressure due to the impact of air. So these are the only two dominant forces, the weight downwards and the resistance of air upwards. And k, of course, varies according to the space, the shape of the body and aerodynamic shape of the body. Rho, the density, varies with height. A, the projected area, the square of the velocity. So we have g and rho, functions of height, as you will soon see. Now here is our mathematical formula. It is mg, the weight, minus k rho av square, as I said seconds before, equals the acceleration m dv by dt. But m dv by dt, we could introduce dx and dx. So you would have dv over dx into dx over dt. We haven't changed anything. We have multiplied by dx and divided by dx. But what we got now, we have got dv by dx and dx by dt. So dx by dt is the velocity v, and dv by dx here. So these two forces equals to mv dv by dx. Nice, very nice. Again, rewrite writing our equation mg and multiplying all through by dx. By dx to get rid of the denominator here, we have mg into dx minus k rho a v square times dx, integrating from v1 to v2 of mv dv dx. We have multiplied both left and right hand side of the equation by dx. The integral, of course, mv dv here in the second step would be m v2 square minus v1 square over 2. But note that here, why can't we perform the integration? Because v square is dx by dt all square. Integrating dx over by dt all square dx is an impossibility. We could integrate the second differential, d2x by dt square, d3x by dt cube, but not dx over dt square. We couldn't integrate it with respect to x. And taking the third step for our equation, mg, taking the x common from mg minus k rho a v1 square dx equals m v2 square minus v1 square over 2, bearing in consideration that k is about 0.28 in our case. Note that k varies with the aerodynamic shape of the body cutting the air or passing through the air. For a modern sport car like this, the k could be lesser than 0.28. It could amount 0.18, 0.2. For an old car like this one in this picture, the k could amount to 0.75 or even 0.8. Let's back to our derivation. The mass of the earth, because as I have said before, the body is falling from very high distances, so we've got to calculate the g as a function of distance. The mass of the earth is 5.972 times 10 to the power 24 kilograms, we are going to make our calculations by using the MKS system of units, where the mass is in kilograms, the length in meters, time in seconds, of course. The radius of the Earth is 6.371 times 10 to the power 6 meters. So, according to the formula for finding the acceleration of gravity, actually the d is from the center of the Earth to the position of the body, which is equal to radius of the Earth plus x, the distance of the falling body from the surface of the Earth. So our d is re plus x. D square is re plus x all square. Actually, this is the general formula to find g. G equals g, the big G, which is the universal gravitational constant, times the mass of the planet, whatever it is, the Earth, the Moon, or whatever planet it is, over the square, the square of the total distance between the centers of the two bodies. Consider x. Why have I started with this x? This x is the neutral point between the Earth and the Moon, where the acceleration of gravity is literally equal to 0. And substituting here, this is an empirical formula for rho, 1.18 e to the power minus 1.865 times 10 to the power minus 5 times x, the distance from the surface of the Earth. Rewriting our equation, mg dx minus k rho a v1 square dx equals mv1 square. We have transformed the mv1 square to here, to the left hand side, equals mv2 square over 2. Why? Because we have transferred the mv1 square to the left hand side, because v2 is what we are seeking. We'll start with v1 and set out to find v2. So mg minus k rho a v1 square into dx plus, rewriting it, we haven't changed anything almost between these two steps, and dividing by, here we have divided by m, g minus k rho a v1 square over m dx. Of course, this quantity has the units of acceleration, into dx plus v1 square equals v2 square over 2. This quantity, as I said, k rho a over m, and substituting for the value of each of these parameters, k rho and a and m, we obtain this quantity. We simplified it to find this value as an expression in x, to have it ready to be multiplied by v1 square. v2 would be equal to twice this expression on the left hand side under the root, because this is v square, all times dx plus v1 square. Now what we are going to do here is to find v2. What would we substitute for dx? The whole distance? No. We'll take small intervals. Why small intervals or small pixels of dx? This is because we've got to have the v1 constant during a given pixel of the dx. Of course, the v1 would be about constant when g and rho are very small, at very great height. Substitute here for a given v1 starting from this distance. Supposing it started from 20 meters per second, 200 meters per second, 0, we substitute for v1 and substitute in this relation, substitute for v1 here and here, and obtain the v2. Now in our second step, dx have been the total x have been diminished, so this x here is diminished by the delta x. Here x equals x minus dx. This is the new x substituted for here. In the next step, we'll consider the v2 obtained as being the v1, and the new x would be the x of the previous step, subtracting it from it dx. So our new dx in the third step would be the first x, the original distance here, minus 2x's, and in the third step we'll take the fourth step, so on. We'll consider the v2 obtained to be the v1 and subtract dx once more from the previous x. So we are going to make all these steps. Can we do this all and subtract 200 meters from this huge distance until we reach the surface of the earth to know what the velocity would be? You will probably tell me it would be a very huge velocity. No, this would not be a very huge velocity. Why? Because while the body is falling, it starts from acceleration of gravity identically equals 0. It will gain accelerations slightly because density of air is equal to 0. But once it reaches a zone where there is high density, it starts to decelerate. Truly, there is the acceleration of gravity increasing or have increased. But at this very high velocity, you would reach a point at a given height where the resistance of air is more than the acceleration of gravity, even when it reaches the 9.8. So it starts decelerating. Truly, it could have reached very colossal velocities. Perhaps it could reach 1500 meters per second. That's this velocity, which leads to very high temperature for the surface of a falling body due to the air friction. Disregarding what happens to the surface of the falling body due to this high velocity, but we are considering now velocity. That's a problem they face in spaceships. What would we do with this high friction that leads to that very high temperature? What we care for now is velocity, that it would be decreasing once the density of air becomes high, becomes remarkable. At the surface of the earth, the density of air would amount to 1.18, because if we substituted with x equals 0, that is the body at the surface of the earth, no height between the surface of the earth and the body, x equals 0 would get rho equals 1.18. And if we substituted with x equal to this distance, we would get rho very, very small, approximately 0. There is a computer program that finishes this equation and resubstitute each time according to your chosen dx. And this computer program is made by me. It could be made by you could find such programs, but not with this wide range of heights and acceleration of gravity. But I have made a computer program for this special case of 0 acceleration of gravity and 0 density. And anyone who is interested in physics, tell him about it and subscribe in my channel if you find this topic valuable. And if you want to discuss the heat here, the acceleration, the mass times acceleration times dx equals mcv dt, or m, this quantity is actually acceleration, m k rho av1 square over m. This is our acceleration unit. dx equals mcv dt, mass times specific heat times delta T. Delta T, delta temperature, of course, the rise in temperature. Substituting in this equation, m into k rho a v1 square over m times dx equals mcv dt. The m cancelled with the m, so would be left with k rho a v1 square dx equals mcv times delta t. So our formula is delta t equals k rho a v1 square over m dx over cv. That is the rise in temperature. You see that is tremendous rise in temperature, especially when rho increases near the surface of the earth. M, the mass of the falling body, v1 square, of course, to be able to calculate exactly the final, we would add delta t for v1 after a delta x, and add to it the delta t in the next delta x. Of course, the delta t at very high distances would be very small. It would be remarkable again when you reach the surface of the earth, where rho increases. Again, delta t, to calculate exactly, I prefer to delta t to multiply this quantity by about 0.5, 0.6, because not all the heat generated from friction with air is taken by the spaceship or by the falling body, whatever the falling body is. Most of this about 0.6 to 0.5 of this energy is gained by the spaceship, and the other is used to heat up the air. That is, the air is heated, but the air doesn't rise, its temperature doesn't rise, because we are not making friction with the same amount of air, the same with the same mass of air. We are moving along from up to down, so each part of the air takes its share. We are not frictioning a given quantity of air. We are taking a column from up to very high distance to down. So the gained heat is distributed all over the very long column from where we started to where we reach the surface of the earth. That's for air, but for the spaceship it is continually rising its heat. So I prefer, when using this formula, to multiply this numerator by 0.6 to find the exact delta T, using small delta x's, 20 meters, and varying the v each time. You substitute in this relation, you find the delta T, add to it the new delta T for the new delta x and the new v. So that's all. Hope you found my explanation useful and interesting. Goodbye.